In this example, we're going to pull together several other cases and put them into one. We're going to take a charged conducting sphere that has a charge of plus Q, and we're going to put it inside of a neutral conducting shell. So the shell itself has a Q equal to 0. So you've got plus Q on the inside, no net charge on this outside. The shaded area is supposed to be the actual metal, right? So let's assume that this is metal. And so this problem is interesting just because it's kind of different. You got a couple things going on. So our goal is going to be, again, to use Gauss's law to find the electric field, and as usual, we're going to use electric field as a function of radius. And that lowercase r is the radius of the Gaussian surface. Okay. Now, I'm not going to draw all of the different Gaussian surfaces, but I'm going to draw one. Let me just draw it here because it's easy to fit it in. And so the idea would be that the Gaussian surfaces that we're dealing with, they're going to be spherical, and they're going to be centered on the object. Okay, so all of these circles that we're drawing are concentric. Okay, so I'm going to write Gauss's law maybe just one time up here to remind us about its glorious truth. There we go. And let's start looking at the different regions now. Okay, so I'm going to have to mark off my inside object with the radius r1. I'm going to mark off my out. Oh boy, we've got more here. I'm going to have this radius. It's going to be my r2. So that's the inside of the shell. And then r3 is going to be the outermost radius of the object. So I've got three kind of fixed radiuses here, and then I've got one variable radius that I use for my Gaussian surface. So let's look first of all at positions which are inside the conductor. So inside core conductor. Okay. And I'm just going to say that for reasons that we've discussed before, the electric field is going to be 0, okay, inside the conductor, and that's because the Q enclosed is equal to 0. So you have to imagine if you draw a Gaussian surface inside of this little object, it will contain no net charge, and that's because all of the net charge goes to the surface. So for the same reason that we talked about before, that's just going to be 0. So when we make our graph here of E versus R, when I go out to R1, the electric field is just a neat 0. Okay, what about when I'm in between? So we'll call that the gap region. Alright, in the gap region, I'll just draw part of a Gaussian surface here. If you continue this all the way around, you'll see that your Gaussian surface is going to enclose the charge of plus Q. And so the electric field in that region is going to be given by the point charge formula. And we've seen that in like 3 other examples so far. So if you have a spherical distribution of charge and you draw a Gaussian surface around it, the electric field outside is going to be given by this formula. And that's because Q enclosed is equal to plus Q. So that's that. Now, the interesting part of this problem is going to be what happens when you're in this range, where I drew the Gaussian surface. Okay. So what happens when you're basically bigger than R2, but less than R3? And here's the thing. This is a conductor, and you have a positively charged object in the middle. These positive charges that are sitting in the middle are going to attract negatives. negatives coming from the shell. And the negatives are going to kind of line themselves up on the inner surface of this shell. Okay? And it'll be the number of negatives that line up around the inside is going to be equal to the total positive charge that you have on the inside object. Okay, so I'm going to make a note here and say that you'll have a negative Q, and that's induced by the positive Q in the core. And the value of that negative Q is equal and opposite to the plus Q that's there. So I'm going to put a little negative Q here to show that. And there's a reason for that. There's a way of thinking about that. So let's just say that you do that, and now you look at this Gaussian surface which comes around. Well, how much net charge is going to be included? Well, the net charge that would be in this Gaussian surface is going to be the positive charge that's here, but that's going to be canceled perfectly by the negative charge that's on the inside. Okay? So the idea would be that in this range, your Q enclosed is equal to 0, and that's because of the induced charge effect. And the result of that, when there's 0 enclosed charge, is that the electric field is also 0. Okay? So inside here, we've got E is equal to 0. Just like inside here, we had E is equal to 0. That's actually important because if the electric field was not equal to 0 in a conductor, charges would actually move, and the conductor would have to achieve some new state of balance. So you'll never have an electric field in a conductor when the conductor is in equilibrium. That's a very important point. Okay, so E is equal to 0 always inside conductors in equilibrium. And the reasoning is that if that wasn't true, is that charges would be moving and you would have a current, and then where would the current come from? And if it was there, it couldn't persist. So if something's in equilibrium, that's the deal with it. So we've got here R2, R3, and the gap, we've got that. Okay, 0. I didn't draw this, but you can add in. This is the function here. Okay, so you've got KQ over R1 squared. And then here, you'll have KQ over R2 squared. And then the last part is going to be what happens for R bigger than R3. So now we'll be looking out here. And the deal here is that when you pull these negative charges to the innermost part of the conductor, an equal number of positives will kind of be left behind, and they're going to come from the surface. So if you had a negative charge induced on the inside, you're going to have an equal and opposite positive charge induced on the outside. All right, so you've induced charges in this conductor. You've separated pluses and minuses, and you have an equal number of negatives here to an equal number of positives here. And by the way, those two Q's are the same as the value of the positive Q, which is on the inside. So when I look at my Gaussian surface that includes all of this stuff, my Q enclosed is going to be my core plus Q plus the induced charges, which cancel out. So this is the core, this is the shell, Of course, those are 0 because there is no net charge on the shell. So once I'm outside of this structure, I've got a Q enclosed, which is back to plus Q, and my electric field is just going to be KQ over R squared. And so then that would be basically like this. It's kind of interesting. It's like the electric field, there's a gap that's cut out of it, and the field will kind of continue here wherever it would have left off if there wasn't a gap there. So my value here would be KQ over R3 squared. So this looks like a, it's like a smile with some teeth missing, right? You're missing chunks wherever there's a conductor. Otherwise, the electric field is just trying to do its job and just do a KQ over R squared type of a thing. So that is the problem, or that is the solution to the problem of the charge conducting shell. And this is a great AP level question where you might be asked to justify and graph, electric fields around in and around this type of arrangement.